Hello, I'm delighted to be joining you from NASA Astromaterials Research and Curation offices. Next slide, please. So, a brief introduction to what I'm talking about. An amorphous ice or glass, and how does it relate to the much more common crystalline form of water? So, I'm sure you're aware, a crystal is a solid that has an ordered, rigid lattice, long form order. Next. Whereas a liquid is disordered and free-flowing. Now, a glass is somewhere intermediate between these, whereas it has a solid structure, and yet it has some disordered character that might be thought of as more akin to a liquid. Next. And this is still a very active area of research. Whereas to quote a recent review paper from 2024, one of the most puzzling challenges is to reconcile physics and chemistry, where molecular physics meets condensed matter physics, resulting from the dynamic fluctuation and scaling effect of glassy matter at the glass transition temperature. And the pioneer of condensed matter physics, Nobel Prize-winning physicist Philip Warren Anderson, referred to this gap as the deepest and most interesting unsolved problem in condensed matter physics in 1995. In Science's 125 Questions We Don't Know, published in 2005, this was still an ongoing problem. And as the 2024 paper states, we still don't have a strong theoretical understanding of how amorphous solids or glasses work. So, to investigate these substances, I will be using an empirical approach. Next slide. And this is important in many different planetary contexts, where at very low temperatures, less than 100 Kelvin, the metastable phase, ASW, is probably the most abundant form of water. And this is likely to occur in the interstellar medium, for example, or next. In a variety of different icy worlds, such as Enceladus, Europa, or terrestrial worlds, Mars, or Venusian hazes, or even the organic hazes of Titan. Next, please. It also commonly occurs within Earth's clouds, so not even that exotic. But all in all, it's really important for understanding metastable phase transitions, supercooled liquids, and volatile behavior across a host of different planetary environments. So, how do we get this? You can imagine if we start with a stable liquid, are able to somehow kinetically bypass ice crystallization via supercooling, then that liquid might continue on to solidify into a glass. Now, once you have this glass, we're interested too in when it stops being a glass, that is devitrification, after which it can go back into its crystalline, thermodynamically stable form. Next, please. And these glass transitions are not just a function of temperature, they're also critically a function of composition. Where you can imagine if you're mixing two different substances with two different glass transitions, TGA and TGB, then the intermediate composition glass transition is going to fall between the two, given that they're miscible and can interact in some way. Whereas if they're immiscible, you would have two different separate glasses. Thank you. Next slide. Okay, and now to the actual research. So to answer this question, where does the glass transition occur for lunar ices, cometary ices, other ices perhaps that we don't have tight constraints on? I conducted a literature review of aqueous organic systems and found that fitting them to a number of different empirically validated models for glass transitions, that they behave highly non-ideally, that some kind of model correction is needed to address hydrogen bonding between the solute and the aqueous system. Next, please. But very interestingly, for small molecules, organic systems in over 60 different systems behave mostly ideally. That is, the hydrogen bonding is not so extensive that you need to correct the non-ideal or the mixing models. So this simplifies things considerably such that, next slide, we can construct a parameter space, conceptualize how these systems might work. Whereas you have water with a glass transition at 136 Kelvin, and then some organic component, perhaps with a glass transition at 90 Kelvin. Then you can imagine either an ideal mixing along the black line or hydrogen bonding that pushes it above the ideal mixing over by the yellow curves, or perhaps some other kind of thinning behavior that might break the glass forming network and push it below. We have competing behaviors, one between the two glass transitions compositions, and then also how they might interact. Next slide, please. So to begin evaluating more relevant cometary and lunar compositions, I looked at the ternary system first for water, methanol, and then some organic, and you can see the different organic components varied in the histograms below. Now, even at this juncture, we start to see differing organic behavior. You can see some have very narrow distributions, some begin to get more broad and bimodal. Also, the water methanol have a non-ideal correction, but some organic systems behave non-ideally as well, and those had more than one non-ideal correction, which is denoted with the stars. Okay, so how does this all shake out? Next slide, please. The long and short of it is that for realistic cometary compositions of water methanol and some very small organic component, it basically converges to a distribution around 133 to 135.5 Kelvin. And that was over about 10,000 different samplings using Dirichlet to constrain the overall composition. Next slide, please. But that was for water-rich ices. So again, cometary averages. But those aren't the only ices that we're potentially interested in. If we start letting the methanol composition increase to be more representative of high abundances found in the interstellar medium or even trans-Neptunian objects with some inferences of composition, then we see that the glass transition overall can get pushed to significantly lower temperatures, maybe 126 to 127 Kelvin for the more water-enriched, or if methanol is getting close to parity, even 113 to 114 Kelvin. This is also interesting for potential lunar ices, whereas the L-cross inferred composition of methanol, and then assuming some very minor organic component, it falls more in line with cometary ices than it would for these trans-Neptunian objects or interstellar medium ice grains. So, in conclusion, next slide. Oh, one more note. So I've been talking a lot about the most metastable version of a glass, but this isn't the only version. So you can imagine conventional equilibrium features on a phase diagram. Next slide. But there also exists an intermediate between a completely metastable state and a completely equilibrated state, which is shown here in B, such that you can have ice and glass coexisting. And this might actually be more realistic for many scenarios. Next slide, please. Whereas this, figure C, is really what the research has focused on right now, the most dilute version of organics forming a glass. Next slide. Now to conclude. So we've produced and validated a glass transition model for both ideal and non-ideal systems, incorporating realistic abundances for cometary and inferred lunar compositions, where those values are mostly going to converge around, again, 134 to maybe 137 Kelvin, such that the organics have a fairly minor contribution. However, if methanol is significantly increased, those can be much lower. Big caveat that this is for the bulk glass transition, assuming one homogeneous system that then undergoes a phase transition. But it may become much more pronounced if you have some kind of fractionation. Thank you.